Today we did reaction with strong acid. We did reaction with BR, and we're finally going to do a reaction with hydrogen and some sort of metal catalyst, or we'll see something a little bit different than this. So these two will be responsible for tomorrow. They're very simple. It's not going to be a major portion of the exam. I'm a reasonably human being. I'm just teaching it to you today. So it's not like tomorrow's exam is going to be 90% alkynes. That would be foolish. It might be a tiny fraction of the exam. And again, I really believe it's a small extension from our work in alkenes. Here's one more series of reactions that we need to do, and I want you to simply memorize these three reactions. What that means is no mechanism necessary, just the conditions. If we take a carbon-carbon triple bond and treat it with hydrogen in the presence of palladium, we very rapidly make a carbon-carbon double bond. And we saw in yesterday's classes that carbon-carbon double bonds, when they're in the presence of palladium and hydrogen gas, go to give alkanes. This is unavoidable. Doesn't matter if you try to add one equivalent of hydrogen. As soon as you make this is very reactive and goes right to the alkane. So we can take alkynes and go all the way to alkanes. If we start with an alkene, we go to the alkane. So this set of conditions takes either one of these types of compounds, reduces them to an alkane by adding hydrogen. Mechanism, not important. Some people realize there would be some utility to stop this reaction at the alkene stage. This is developed by someone named Lindlar. They got this reaction named after this. There's a couple ways to do it, but if you take palladium, this example was on carbon. If you take palladium and put it on a salt like calcium carbonate, the reactivity of the palladium drops off a little bit, and we can actually stop this reaction here. Okay? So we can just modify this a little bit, and we can go to here, or we can use the original conditions and go to here. There's a very small amount of new material. And there are some stereochemical consequences for this last reaction that we just put in our notes with Lindlar's catalyst. Name is not important. Part you need to memorize is that H2, palladium, and calcium carbonate. Or if you studied something else in the textbook, I'll know it when you put it on the exam. But these conditions are enough for us this semester. If we actually use these sets of conditions, we get 100% cis stereochemistry. This is the result of syn addition, where both groups that are coming onto it go on from the same side. We did actually draw this a little bit into our notes, but it's not really necessary for us to work out mechanism of this sort of stuff. I'm not going to ask you about this. And there's one other alternative way to make the trans alkene. It's very, very different. The mechanism is a radical reaction, and we're not going to go into it. But the conditions I need you to know, that sodium metal, so this little zero means, sodium metal in liquid ammonia can reduce this to 100% trans stereochemical products. Reactions for these two things are quite complex. Never ask students these things. I can take any time to even describe this particular reaction for us. But when you take sodium metal, which is very dangerous, if you throw this in water, it will be the 4th of July instantly. I hope you're outside and far away from anyone. When you add it into ammonia, solution starts turning blue as electrons jump from this into ammonia, into solution, and become solvated, and the solution glows blue. It's pretty cool. Maybe some of you will get to see that once in your lives. Or twice, or maybe you'll do it every day of your life. I hope not, though. So that concludes the the content of what we're going to